let's get started. Today we will continue our discussion of probabilities and in particular probabilistic machine learning methods. We'll cover naive Bayes. And let me begin by a quick review and kind of mentioning some terminology also that covers the discussion that we had of last lecture. We were talking about the question of how to use data to estimate probability terms. And we talked about two, of course, as you remember, we talked about two particular approaches to doing that. One approach, which we call the maximum likelihood approach, is to follow the principle that the value we want for the probabilistic parameter, that's theta here, is the value of theta that makes the observed data, that's D, as probable as possible. And then we did some work to show that if we do that, we get a particular algorithm that many of us would have thought of anyway for how to estimate the probability, for example, of a Boolean variable that can have values 0 or 1. And then the second approach we talked about, the maximum a posteriori probability approach, is to instead choose the value of our probabilistic parameter that we're trying to estimate, which is itself most probable. And to do that, we use Bayes' rule so that we end up being able to ignore the denominator here, of course, because it doesn't really depend on theta. But the numerator does, and so we end up choosing the theta that makes this data likelihood, same as we were using up there, times some prior, as large as possible. And those were the two approaches we talked about. I want to just go through a quick summary of this again because it's going to be very important. We're going to use it later on in this very lecture. So in general, and I'm using this also to introduce a little terminology that you will see in papers if you read the machine learning literature. So in general, we were talking about coin flipping, and we said, well, we have a random variable, x, can take on values 0 or 1. In general, and we will describe its probability distribution by a single parameter, theta, which is just the probability that it will take on the value 1. And of course, since the probabilities must sum to 1, that's the only parameter we need to estimate because we know the probability that we'll take a value 0 is just 1 minus that. So in general, that kind of random variable that's Boolean value and whose probability distribution is determined by the single parameter theta is often called a Bernoulli random variable. It's Bernoulli because of the values it can take on and because of the way we represent the probability distribution. And then we calculated when I asked you, we calculated when I asked you if we flip it or draw a collection of samples from that random variable, and we notice that we get alpha 1 times when it has the value 1 and alpha 0 when it has the value 0, then here was the formula you told me we could use to represent the probability of this observed counts in our data. And so then the maximum likelihood estimate, we did some calculus to figure out that the value of theta that makes this most probable is actually just this, which fortunately jives with our common sense notion that we should just look at what fraction of the coins end up being a head flip compared to the total number of flips we did. And in fact, that provably does give us the maximum likelihood estimate for theta. Okay, now, it seems like I'm belaboring this, which I am. But the reason I'm belaboring it is many machine learning algorithms that we're going to design are going to have multiple probability terms that we have to estimate. And so we'll think of theta as a vector of probability parameters in general. And we're going to follow this, in many cases, exactly the same principle. We're going to want to design a more sophisticated learning algorithm that can output the collection of parameters for our learning system that jointly make the observed data most probable. Okay, then we also talked about the map estimate. And again, for our Bernoulli random variable, we decided we would use a beta prior to represent our prior knowledge about this random variable, in particular, the probability distribution over theta. And then when we work out the map estimate, which maximizes our old friend, the data likelihood, times this new prior, we found that the value of theta that maximizes this product is actually this. And so we can interpret this as though we're adding in beta 1 minus 1 hallucinated imaginary examples of coin flips where the answer is x equals 1, plus beta 0 minus 1 imaginary flips where the outcome is x equals 0. Those were the two algorithms we talked about. I went and made a plot because I wanted to say something in addition that we didn't really point out, but the more astute among you probably have already figured it out, which is we talked about getting a point estimate for theta. That is, we talk about getting, well, what's the most probable value of theta given the observed data and perhaps our priors. But in fact, Bayes' rule gives us a whole probability distribution over theta. And what we solved for when we got the map estimate was actually just the most probable value. So here's what the full story really looks like. Suppose that I want to get a map estimate for theta, and I decide to use this prior. I'll call this my P of theta. This is my prior on theta. And this is, in fact, it says right there, the probability of any given value of theta, which of course can range from 0 to 1. It's got to be a probability, so it's got to be between 0 and 1. And according to the beta distribution shown up there, and in this particular plot I've chosen beta 0, or I could say beta tails, equals 3, and beta 1, or I could say beta heads, equals 4. So it's as though I'm hallucinating in this prior that I'm synthesizing 2 flips, 3 minus 1, for which it's tails, and 3, 4 minus 1, for which it's heads. And then this is the prior probability distribution over theta, defined by that beta distribution. Of course, I can make up different beta distributions, and when I talk about beta distribution, it's really a family of probability distributions. It's parameterized by beta 0 and beta 1. I can pick whatever I want for those. But if I pick beta 0 and beta 1 to be 3 and 4, respectively, then here's the distribution. Okay, so now suppose I observe a 100 coin flips, or 100 draws of my Bernoulli random variable, and I get 50 for which x equals 1, or heads, and 50 for which x equals 0, or tails. Then I want to know the probability of theta given that observed data. This is my observed data here. And as we said, that's proportional to the probability of the data given theta times the probability of theta. this is my distribution for the prior. This is actually my distribution for the posterior probability. We call this posterior in the sense that it's after we have seen the data, as opposed to the prior, which is before we've seen the data. And what's wonderful about this, remember, is that this term here was just theta, I guess, to the 50 times 1 minus theta to the 50. That was the probability of this observed data given theta. And the probability of theta, of course, is just this, the prior probability. And when I multiply these two things together, what you see happened is that up here and here, these quantities got multiplied so that all I have to do is see that I can represent this just by summing the exponents. So it's 50 plus beta 1 minus 1 is the probability here. But the important thing is this probability distribution itself is also a beta distribution. It's just a beta distribution where instead of having B0 and B1 be 3 and 4, they now are 3 plus 50 and 4 plus 50. And this is, in fact, the beta distribution for beta 0 equals 53 and beta 1 equals 54. So, in a nutshell, what's happening here is this P of theta represents our prior assumptions from whatever source. There's no science behind it. We just have to search deep in our soul and come up with what we think the prior is on this. But then once we see the data, Bayes' rule tells us we can calculate the probability distribution over possible values of theta, given that observed data. And because we've chosen this beautiful functional form called the beta family to represent our initial prior, when we get done multiplying that prior times the data likelihood, we end up with another beta distribution. Only this one is centered somewhere else because it's been influenced by this. And it's tighter in this case, intuitively, because now we have some evidence. We have much more evidence than even we hallucinated in our priors. So in general, what happens is, if we use Bayes' rule to get this probability of theta given the data, what we're really doing is we're getting a whole probability distribution which tells us how probable it is that the real theta, given our priors and the observations, that the real theta is any particular value between 0 and 1. And then the map, the M in map, stands for maximum. And so our map estimate will be exactly the value of theta right there, because that corresponds to the top of the curve. And in fact, that's why we solved for the derivative being 0, because the top of the curve is, fortunately, the only place in this curve where the derivative is 0. Okay? So it's actually very principled and very straightforward in a sense what we're doing. We're just saying Bayes' rule lets us get the probability of theta given the data as the product of these two terms. And then we purposely chose to use a beta distribution to represent this term because it's in a similar functional form to the data likelihood, and the parameters of the beta distribution, beta 0 and beta 1, are conveniently defined to go along with our intuition so that we can treat those beta 0 and beta 1 parameters as capturing our prior intuitions in terms of imaginary examples. I want to say one more thing, then I'll come to you. The one thing I want to say is, whenever we have this situation, namely, we have some random variable and some parameters we want to estimate, one or more. If we choose a prior that has the property that the posterior will also be from the same family of distributions as the prior, as it is here, the posterior is a beta distribution just as the prior is, then we call that the conjugate. We say the beta distribution is the conjugate prior for our random variable. It's the conjugate with respect to the data likelihood, meaning it's in the same functional form as the data likelihood. And the example we're doing here, where we flip a coin, is a Bernoulli random variable governed by this kind of distribution, and the beta is the natural conjugate prior for that, because you can make up your own conjugate priors, in fact, just by writing down what the data likelihood looks like, and then say, okay, I want the prior to look like that too, and then you add a normalization term like this denominator, just to make sure that the probabilities over all possible values of theta integrate or sum to 1. So, and we'll be doing this kind of throughout the semester. Okay, long suppressed question. Yes?
That's fine. I thought the base formula required that the elements on the right need to be divided by P of D.
Right. So the question, I've been asked to repeat the questions. I'll try to remember. If I forget one, shout out. The question was, Bayes' rule tells us we have to divide this quantity by the probability of D, P of D. It's true, and that's why instead of writing an equals here, I put a proportional to sign. And the reason I didn't bother to draw the P of D in here is that when I maximize theta, P of D is independent of theta. So it's not part of the optimization problem. Yes?
So if we're kind of observe a data set where we have, let's say, 50 heads and 50 tails, should the probability of like having 50 heads be like theta to the 50 times 1 minus theta to the 50 and times the number of permutations in which you can have like 50 heads and 50 tails?
That's good. We're making the assumption that these draws from our Bernoulli variable, our coin flips, are independent. And so the probability of the set of observations doesn't change if we change the sequence of observations.
Right, but all those possible sequences would have the equal probability of occurring. So if a random variable is just the count of the total number of heads, then should we take the number of permutations into account?
Because, so the question is, don't we have to take into account the number of different sequences in which we could get 50 heads and 50 tails? And the answer is we don't in this case, because of the assumption we're making about independence. We can talk about it more offline. There are plenty of probability distributions where you have to normalize by those kinds of things, but here we do not. Okay, so this is kind of review, but also I think this picture for me helps to summarize. If I had 4 big pictures that I carried around in my head instead of 3, I might add this one as one of the candidates for number 4, because it kind of summarizes very simply that what we mean by prior is really assigning a probability to each possible value of the thing we're trying to estimate. And what we mean by a posterior is, again, something that will tell us the probability for any possible value of that. It's just their different probabilities. Okay, so conjugate priors. One more thing I want to say about this. It's interesting to think about, what if we didn't have just a Bernoulli variable that had two possible values, but what if we had something that had more than two? So in that case, there's a very simple extension to the analysis we did. This would be a good thing for you, like, if you want to dig deeper in this, this would be a good thing for you to derive the maximum likelihood and math estimates for. But if, for example, if we have a die with 6 faces instead of a coin with 2, then we say, well, we need to define the probability of different values. So we say, well, the probability that the dice ends up being a 1 is, we'll call that theta 1, and the probability that dice equals 5, we'll call theta 5, and so forth. We'll do all 6 of them. Do we really need 6? We had a coin with 2 sides, but we only needed 1. Yeah, I mean, they have to sum to 1. You roll the die, it's got to come up something. Just like when you flip the coin, it's got to come up one of the 2 values. And because the coin had to come up one of the 2, we didn't really have to estimate both the probability of heads and the probability of tails, because we could express the second one in terms of the first one, 1 minus it. And so what if I actually want to represent this distribution and I was in favor of simplicity instead of efficiency, then I might assign 6 parameters that I have to estimate, theta 1 through theta 6, and each one would represent the probability that the die comes up, one of those 6 values. But of course, those probabilities have to sum to 1. So I could not bother, for example, with theta 6. I could just say that's 1 minus theta 1 minus theta 2 minus theta 3 minus theta 4 minus theta 5. Right? So they're not really independent. Okay, but that's kind of a efficiency thing that will be useful to us later. But now the probability of any observed set of die rolls, I roll it 100 times, and maybe I see 6 times that it comes up with a 1 and 12 times it comes up with a 2 and so forth. My data likelihood is very similar to what our Bernoulli variable was. And the conjugate prior for this form of data likelihood looks like this, which should be no surprise now because we understand how you make up a conjugate prior. You look at the form of the data likelihood and you say, gee, I want a prior that looks just like that, so that when I multiply my prior times this, I'll end up with another distribution that's of the same form. And so we could boutique design this to be the prior, given that that's the kind of data likelihood we have. And sure enough, that's called the conjugate prior for this multinomial distribution. That's what the dice is. For the die-like multinomial distribution, the conjugate prior is, in fact, the Dirichlet distribution. Okay, so it's a very simple idea, but you can see how you could kind of stamp this out if I gave you another kind of random variable or even a pair of random variables and gave you some formula for calculating the data likelihood. You could probably make up an appropriate prior. You always end up having to put some normalizing thing down in the denominator just to make sure that all the probabilities sum or integrate to 1. But other than that, it's pretty straightforward. Yep?
Other question is, how we determine whether we should minus 1 or not from alpha 1 to beta 1 minus 1?
Good. How do we decide if we should put a minus 1 here or not? I find it incredibly annoying that the statisticians have put -1s there. If I got to make up priors, I would not.
So you would like to add +1 after in the
Put a +1?
in the later, for example, in B parenthesis.
Oh, then we'd have to put a +1 here.
Yeah.
Maybe you're right. Maybe that's why the statisticians did it. I thought they just did it to trick me, but maybe you're right. Maybe we'd have to end up with a 1 there. That's pretty good. Okay, maybe those statisticians are smarter than I am. Okay, that's all I really wanted to say about Dirichlet distributions, but they will come up again too, and so will some others we'll be talking about. Yep.
Finally, when you're choosing priors, what extra benefit does choosing a prior that is a conjugate prior give us in our combination? Like, why do we want to have a conjugate prior? What additional benefits?
Oh, why do we want a conjugate prior? For one thing, it does a couple things for us. Given that this data likelihood really depends on observations that we're summarizing here in these alphas, in general summarizing in what we tend to call sufficient statistics from the data, if we make up a conjugate prior whose parameters map onto those, then we end up with a formula where we can think of these parameters in terms of being hallucinated data with certain properties. So that's one thing it buys us. It also buys us, if you think about it, a kind of incrementality. Suppose I want to be careful what I say here. Cancel that. I want to think that through before I say it in public. Especially on video camera. Man, I'm nervous about it. There's more one could say. Okay, so to summarize all this, here's what you should know. You should know about random variables, conditional probabilities, and all these joint probability distributions we talk about. Bayes' rule, calculating probabilities from joint distributions. You should be able to do all those things, for example, on a midterm. You should be familiar with these two key approaches to estimating probability parameters from data, and with these basic distributions that we've just talked about, and the notion of a conjugate prior, which simply is that the prior is the same functional form as the data likelihood and therefore the prior, the posterior. Okay, but now let's move on. Well, let's see. Does anybody have questions or comments about this part before we move on? Yes.
So we were talking about the data distribution first in 79. We're not starting with that. What happens to those loaded die and where the distribution changes? Would that make the classified or
Okay, so the question is, what if we had, back to the distribution that represents a die, what if it's a loaded die? Now, if you mean that there's a piece of like real heavy uranium in one corner of the die, for example, that makes it come up 3 or 4 more often than it comes up the other numbers, then that's no problem. Just like a coin that doesn't come up 50-50 is no problem. We ended up in our definition of the multinomial distribution, that's why we assign a different theta for each of the k sides, so that we can actually, from the data, estimate and notice that, oh, 3s and 4s come up a lot more than the other numbers. So that's not a problem. The thing that would be a problem is if we did something weird to the die so that it was no longer a stationary distribution, so that then maybe I roll the die, and inside there's a little circular track where the heavy uranium can move around depending on how the die landed last time. That's a problem, because now the die rolls are no longer identical and independent, distributed identically and independently. And so then nothing we've talked about applies. But as long as it's a fixed distribution, then we can estimate whether it's a fair die or a loaded die in one direction or another. And in fact, that's the virtue of this. Yes?
What is exactly representation of V, Francis, beta 1, etc.?
Oh, the representation of this? I can't even write this down off the top of my head. I would just say that what it does is it makes sure that if you integrate over all the possible values of theta 1 through theta k, if you take away this denominator, if you think about it, you need that this, in order for this to be a probability distribution, the integral over all possible values of these k parameters has to integrate to 1, probability mass 1 total. And so if you take away the denominator and you do that integration, that's what the denominator actually is.
It's for normalization.
It's a normalization. So you could I think of this function as the integral from 0 to 1 of theta 1, theta 2, theta da, 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 up to theta k of this numerator. And then I want that to be 1. Okay. All right. So now let's move on to actually learning classifiers and training them. We talked also recently about joint probability distributions. And we talked about the fact that once we have one, we can basically treat it as a probabilistic classifier, right? If I want to predict what's the probability that you're wealthy, given your gender and the number of hours that you work, then I can use this to, for example, calculate those conditional probabilities. So now if I have a new test example, a new person walks in and says, well, I'm male and I work more than 40.5 hours a week, then I can say, you're probably poor. In fact, the sad thing here, as you can see, is that even without asking you the question, I can probably say you're probably poor. All right, but you're not as poor as that female student who walks in who works less than 40 hours a week. They're even more probably poor. This was old data before the world started. It's still true, but it's hopefully getting less true over time. Okay, so what I want to do the rest of this class is talk about a Bayesian classifier called naive Bayes, which is very practical, and then try it out on a real example, see how it works. Okay, so let's think about it this way. We've talked before about the problem of estimating the joint distribution. The practical problem being that there are a lot of entries in that joint distribution, and unless we have a lot of data, our maximum likelihood estimates might not turn out so well. And if we use map estimates instead, then we're relying a lot on our priors instead. So just to kind of get a feel for that again, if I have, in general, a table with, let's say, n plus 1 entries, and one of them, they're all Boolean random variables, and I want to pick one of them to be the variable I'm predicting, I'll call that y. And the other n variables will be the things from which I do the prediction. So I'm interested in the probability distribution over y, like wealth, rich or poor, given the other variables. And in general, if I have n of those, how many parameters would I have to estimate in order to learn this conditional distribution? Right, 2 to the n. So for every one of, I could build a table like the one up here that said, well, I'll condition on gender and hours worked, and I'll predict the other variable, which is wealth. And so looks over here like I have 8 numbers, right? That's because the n equals 2. So in general, how many do I need here? If I want to represent P of y given x1 through xn. Right, so here I have n equals 2. So I have 4 rows. And I have 2 numbers for each row, but you can see that the 2 numbers add up to 1. So, like, you know, the bottom row there, you're either rich or poor, so one of those probabilities, 0.62, is just 1 minus the other. So I need to estimate 4 in the case of 2, or 2 to the n. Right? Right, so for each of the 2 to the n permutations here, I need the probability that y equals 1, and the probability that y equals 0 is just 1 minus that. So we need it. And as we said before, if we have 100 of those, then it's real bad. Because 100, 2 to the 100th, as we said, equals 10 to the 30th. It's bad. We'll never get 10 to the 30th examples. So maximum likelihood estimates of these 2 to the n parameters are going to be a problem for us if we have large numbers of variables. So what can we do? Can Bayes' rule help us? Well, here's Bayes' rule again. And by the way, notational thing. The first time I saw Bayes' rule, I was confused. What does this stuff mean, that the probability of some variable is given some other variable? What does that mean? Don't we have probabilities for variables having values? What does it mean to have a probability of a variable? Was the first thing I thought. And so then later I realized that's just shorthand notation for this. So when I say the distribution of P of y given x means for every possible I and j, the probability that y takes on its ith value, given that x takes on its jth value, is this quantity. And then that suddenly demystified for me what this notation really meant. So whenever I see that, I just mentally translate into this, and now I don't get worried anymore. And here's just a rewrite of that using the fact that the probability of x taking on a particular value is just, if I have a joint distribution between x and y, then that's just the sum over the values y can take on. It's basically the expected value of x given y. Okay, so this is just equivalent to that. And we will often find this a very useful way, like today, to write Bayes' rule. Okay, so now, how can we reduce the parameters? We already had this slide somehow. The answer we're going to use is something called naive Bayes. We're going to make the following seemingly insane assumption. We do know that, from Bayes' rule, we said the probability of y given x1 through xn, which is what we want, is the probability of x1 through xn given y times the probability of y over the probability of xn. this quantity here, we're going to assume that for any given value of y, the probability of x1 through xn taking on their values is just the product of their individual probabilities. In other words, we're going to assume that x and xi and xj, these different x's, are independent, actually we're going to say conditionally independent, given the value of y for all i's and j's. Okay, so think about that. What does that mean? It means, like, for example, if I suppose I and j were the language you speak and the language your parents speak. And I'm trying to predict, I don't know, some y, like the color of your eyes. It's like saying the probability that you speak English and your parents speak English, or that you speak Chinese and your parents speak Chinese, is just the probability of somebody speaking English times the probability of their mother speaking English, of a mother speaking English, which is certainly not true. Those are not independent things. You and your parents often speak the same language. So it's a crazy, blindingly unrealistic assumption. But we make up for that by the fact that it gives us a tractable number of parameters to estimate. And it turns out to be a surprisingly effective probabilistic learning method in practice. So let's look at, when I say conditional independence, what I really mean. I'll often write it this way. I'll say x is conditionally independent of y given z if the probability distribution on x given y and z is no different from the probability of x given just c. Or expanded out in my, I think, more obvious notation is this. So for example, suppose I have 3 Boolean variables. Is there thunder? Is there rain? Is there lightning? I would say to you that it seems to me the probability that thunder is true or false, given that I know the value of rain and the value of lightning, is no different from the probability that thunder is true or false, given that I know whether there's lightning. In other words, I don't think knowing whether it's raining, once you already know that there's lightning, adds any more information about whether there's going to be thunder. And for that reason, what I'm saying is thunder is conditionally independent of rain, given that we observe lightning, or not, given that we observe the value of lightning to be 1 or 0. If there's no lightning, there will be no thunder. If there is, there will be, if you're close enough. But whether it's raining or not won't actually change that. Okay, so this is what conditional independence means. Much of the practical use of probabilistic machine learning methods is based on bringing in prior knowledge of this type to allow us to represent joint probability distributions with many fewer parameters based on introducing equivalences like this. Okay, so let's look at naive Bayes. If we say that x1 and x2, or x1 is conditionally independent of x2 given y, in other words, this, then what's it trying to do here? P of x1, x2 equals x2 and y times the probability of x2 given y But if I make this assumption, then it says I can re-express this as just p of x1 given y. So basically it says for any, here I have only two x's, but basically what I'm saying is the first line follows just from the chain rule, right? But if I make the conditional independence assumption, then I can represent this way, the first term. And so in general, the probability, all right, so moving right along, in general, we're going to make the assumption that all the xi's are conditionally independent given y, and therefore this term can be expressed just as the product of many simpler terms. But now the beautiful thing is, whereas before we needed roughly 2 to the n parameters to represent this, actually 2 times that, because we need one for the case where y equals 1 and one for the case where y equals 0. How many parameters are involved here? Remember, y can be either 0 or 1. That's why we needed 2 to the n. When y equals 0, we need 2 to the n to represent, for example, the probability that each of these are 1. And of course, 1 minus that is the probability that they'll be 0. But then we also need, for the case where y equals 0, the whole thing again. So that's why we needed 2 times that. Here, again, when y equals 1, how many parameters about xi do we need? 1 each. So if we have n parameters, we need n for y equals 1. We need another n for y equals 0. 2n. So we went from a number of parameters that's exponential in n to a number that's linear in n. So it's a huge reduction in the number of parameters used to represent this distribution. Now, the trade-off here is real. We're trading off, with this representation, we could, have the whole joint probability table and assign a different probability to every single combination of features. Whereas here, when we shrink it to something we can represent in terms of just 2n parameters, there are going to be probability distributions that we could represent here that assign probabilities to joint assignments of x1 through xn in different ways that we're just not going to be able to capture with only 2n parameters. So we're sacrificing expressibility in representing the true probability distribution in exchange for getting a cut on the number of parameters we're actually going to estimate. And that's the trade-off. Now, this trade-off is a good one if you're in the situation of having a lot of x sub i's and not a whole lot of data. And that's often the case. Okay, so here is the naive Bayes learning algorithm. It's called naive because we are making this naive assumption about all of the xi's being conditionally independent given y. And so we start with Bayes' rule. Nothing suspicious there. Bayes' rule is the most trustable part of probability. But then we assume conditional independence among the x sub i's. So what that means is that we can rewrite this term as this term. Right? That's where we're saying that thing can be expressed as just the product of a bunch of individual probabilities. And then, of course, we do it also in the denominator. And then if we want to pick, so if we estimate all of these terms, these 2n terms, if y and xi are all Boolean, plus we need one more term for what's the prior probability that y is 1 or 0, or the marginal probability, if you like. Then when we get a new example, a new x, we just look at the features of the new x, we calculate the probability that we would see all of those features given that y equals, let's say this could be 0 or 1. We calculate it for the case where y equals 0 times the prior probability that y would be 0. And then we calculate it again for the case where y equals 1. And then we take whichever one of those assignments to y gives us the greatest probability, because the greatest of this will be the greatest of that by Bayes' rule. Okay, so that is the naive Bayes algorithm. And fortunately, we have time to try it. So here it is again, where we're going to train a naive Bayes classifier by estimating the prior probability of y, and then for each x sub I, estimate the distribution of its values. So here's the problem I would like to try it on. Here's the problem I'd like to try it on. So you will all be training examples, and we will learn to predict which of you lives in Squirrel Hill, given 3 variables that represent you. One is, these are all Boolean variables. One is if you shop at the Squirrel Hill Giant Eagle. One is if you drive or carpool to CMU, 1 or 0. And 1 if your birthday is before July 1st or not. Okay, so let's get started. I have pre-selected several assistants in the front row to be my counters of training data. We will use maximum likelihood estimates for all the probability terms we need to estimate. And I have selected a kind calculator to bring together these counts into numbers for us. Okay, the rest of people, if you're in the front row, please do not answer any of the training questions, because you will be our test examples. Everybody else in the room, you are a training example. Okay? And let's see. So in a nutshell, here are the probability terms we need to get, right? We want to find, let's go back to our slide. We need these parameters during training, because when we go to classify the people in the front row to find out, do they live in Squirrel Hill, yes or no, what we're going to do is pick the value of yes or no for y, which maximizes this quantity. And so we're going to, under the assumption yes, look at their properties, like do they carpool to CMU and so forth, multiply those together, multiply by the prior, and see whether it turns out higher under the assumption that y equals 0 or 1. Okay, so back to this. Therefore, we need to know what's the prior that s equals 1. That's the variable we're trying to predict, right? And, oh, this one's even better. This is what I thought we were going to do, but when the slide came up the other way, I was surprised. If you walk or bike to CMU. Okay, so counters, please stand so that you have a good view of your portions of the training examples. I'll warn you that if you stand in the focus of this, you get blinded, but you can. Okay, and please go to your respective parts of the room, and I will ask first, among the training examples only, no front row people, please raise your hand if you live in Squirrel Hill. We're getting the priors on S. Okay, everybody count your respective parts and then shout out the numbers. 6, 7, 13, 10, 23. Approximate. 17. Okay, 17 plus 23 is 40. Okay, and how many people do not live in Squirrel Hill? Count, please. Same number I got.
28,
Thank you.
31,
21,
31.
31.
$35.
35, good. My calculator reveals that this is 48, 79, 114. Okay, so the prior probability of living in Squirrel Hill is 40 over 40 plus 114. My calculator can work on the decimal number for this and let us know. Meanwhile, let's move on to training on the probability. Now, if you're a training example, first, don't raise your hand unless the condition S equals 1 is true. Condition on the assumption that you do live in Squirrel Hill. Then raise your hand if and only if you walk or bike to CMU. And the definition of this is if you have walked or biked to CMU at least once since July. So I'm getting this next probability term. Okay? 1, 2. You see the question? If you live in Squirrel Hill and you walk or bike to CMU, raise your hand. Okay. 1, 2, 3, 4, 5, 6, 7. Wow. Okay, 7 the number? Okay, so 7 out of, what was our total number of Squirrel Hill people? 40. Okay, so we need that number too. My calculator can work on that. Okay, and now if you do not live in Squirrel Hill, let's get the next one. If you do not live in Squirrel Hill, but you walk or bike to CMU at least once since July, raise your hand. $13?
20.
28? Oh. That was here. My counter can give us the answer. Do you know the 0.81?
No, the first one?
Yeah.
0.26.
Oh, the first one is 126, 0.126?
No, 0.26.
I see, 0.26. Okay, and the second one?
0.175.
0.175. And the third one? Oh, we have to normalize by, oh, this was 114 over 40 plus 114. So this third entry would be this sum divided by 114. Okay, let's move on. We're making progress. Now, the probability of, we're interested in the probability of shopping at Giant Eagle given that you live in Squirrel Hill. So if you do live in Squirrel Hill and you have shopped at Giant Eagle since July 1st, raise your hand. Okay. And again, this is given that you do live in Squirrel Hill, which is 40 people. Okay. And almost finally, we're interested if you don't live in Squirrel Hill and you have shopped at Giant Eagle since July 1st, please raise your hand. Six. Okay. Sorry, the last one, 11. And again, this is normalized by 114. Okay, and then walk or bike to CMU. Wait a minute. Oh, no, this is birthday. This is birthday. Now, if you live in Squirrel Hill and your birthday is before July 1st, please raise your hand. 2 plus 4 plus 1?
5.
And 5? 7 and 5? Wow. Over 40. Is that about, can this be? 18 people out of 40? Okay, that's close to 20. Okay. And now, if you do not live in Squirrel Hill and your birthday is before July 1st, please raise your hand. 7.
6, 5.
6 plus 5.
16.
12.
16, 5, and 12. Is that right? 7, 16, 5, and 12? Okay, and that's over again 114. Okay, now, by the way, why did I have to ask on this one instead of just taking 1 minus that? Yeah, those things don't sum to 1, right? What sums to 1 is this probability plus this probability. In fact, we can compute all the ones on the right as 1 minus the term that's on the left. So we're done training except for getting a few numbers. Would my calculator be ready to reveal the numbers? Okay. Maybe I'll write them on this side. So we already have 0.26. 0.175, and what else? .71, and sorry, 0.85, 95.
0.35.
Great, thank you. Okay, so now I'm going to get rid of all this stuff to create some white space. And of course, now we know all the probability. We just trained a naive Bayes classifier. We now, the last one was 3.5? Thank you. All right. So now we know all of these things. Oh, I guess I didn't. Oh yeah, this, if that's 0.26, then this is 1 minus 0.26, which is 0.74. This one would be 0.825. This one would be 0.29. This one would be 0.05. This one would be 0.65. This one would be 0.55. This one would be 0.65. Man, okay. All right. All right, now, what should we do? Is there anything else we have to do to train this? No, we're done. That was it. We just had to estimate those probabilities. And now through the magic of the naive Bayes assumption, we want basically y nu is the argmax over possible values of y, let's say 0 and 1, of the probability that and instead of y, I'll just use the real value, which is, or the real variable, which is, do you live in Squirrel Hill, which is just the prior probability. I'll write times the well, I guess I have to write them all out. Times the product of over all my x sub i's, which are w. So given a new test example, we're going to see what their w new value is, what their b new value, and their g new value. And we're going to want to know the probabilities of those given S nu, given that S equals S nu. And so we want that for W, we want it for G. I'll just put dot because I'm running out of room. And B. Okay. So who would like to be the, I'm not putting you on the spot, but it's really important to me that the new test example be correctly classified. So can I have a volunteer, please, from the test set? Okay, sir. Now, do not reveal, of course, the value of S, but please tell us your W and your G and your B values. Is what? 0? Okay. Okay, I'm having a good feeling. All right, so now we have to calculate. What do we have to do? We have to calculate this thing for both lives in Squirrel Hill equals 0 and equals 1, right? So for the case where S equals 0, then we have what? The prior probability of S equals 0 is 0.74, right? And the probability, given that S equals 0, that W equals 0 is 0.29, right? Correct me if I get this wrong, because it's really important. Times the probability that G will be 1, given that S equals 0, which is 0.35, times the probability that B will be 1, given that S equals 0, which is 0.35. Okay, and my calculator assistant may work on the product of those four numbers while we write down the thing we want to compare it to, which is under the assumption that S equals 1, then the prior, of course, is 0.26 over here, times the probability that W will be 0, given that S equals 1, that's right here, 0.825, times the probability that G will be 1, given that S equals 1, which is 0.45, times the probability that B will be 1, given that S equals... That's this one, right?
Instead of 4.
Sorry?
The third is 0.95 instead of 0.45.
Oh, wow. Yeah, thank you. What did I write down? So probably the G1 given S equals 1 is 0.95. Thank you. And Finally, the probability given S equals 1 of B is 0.45. Okay. I look at these numbers, I can tell which product is larger, and I like it. I don't know the S yet, but I'm thinking it's compelling probability. Okay, so is our calculator ready? Okay, the first product is 0.026 versus 0.91. Okay, why don't those two numbers add to 1? Yeah, they're not probabilities. They're just this rule for looking at the numerator and Bayes' rule and that. Actually, if we wanted to turn them into probabilities, then looking back at Bayes' rule, you can see that what we want to do is take 0.026, that's, say, the quantity associated with the assumption that S equals 0, and divide it by 0.026 plus the other number. So if our calculator could give us that, it would be helpful. Sorry? 0.22? Okay. And so I determined that the probability that, that's the probability that S equals 0, and so the probability that S equals 1, given those same things, is 1 minus that, 0.78. Okay, now, so according to our naive Bayes classifier, not only is it more probable that S equals 1, but the probability is 0.78. And 1 minus that is the probability that S equals 0. And the answer is, yay, all right. I can't tell you how many times I've run this experiment and failed. You're helping my win rate. Okay, so the important thing here is, of course, not what happens on a single test example. I will get a piece of paper and ask all the other test examples to write down their 4 values so that we can next lecture start by revealing how well we do on a more representative sample. But we're off to a good start. The point of this, if you get anything out of this lecture, is that here we are doing a very practical probabilistic learning algorithm, in this case naive Bayes. You can see, having done it, exactly how straightforward the training is. It's a matter of counting probabilities, and then through the assumption of conditional independence, which naive Bayes makes, we get to use those terms to estimate probabilities for labels of future examples. So the homework will give you a chance to work with some of these things too. So see you next time.